Polynomial functions and models. Today's lesson is just going over some basic parts of polynomial functions and some key things that will help you with graphing. So to start with, we need to talk about the terms of a polynomial. The terms in a polynomial are in descending order by degree. The degrees decrease from left to right, and this order demonstrates what we call as standard form. All right, some key terms throughout a polynomial. Right here. This number is called the degree of the function. The degree of the function is always the highest degree. This number is called the leading coefficient. All right, and I'm going to abbreviate this as LC. We write it kind of a lot, so LC will stand for leading coefficient. And then just to name a few terms throughout this expression, this term right here has a degree of 3, so we're going to call this a cubic term. Obviously, this changes with the different degrees. This term right here has a degree of 2. So we're going to call this a quadratic term. Linear term. And lastly, we have a constant term. So the constant term is the only term that doesn't have a variable with it. I guess technically you could say it has a variable raised to the exponent of 0, which is just 1, but we never write that. So the constant term is the term that is by itself. Okay, this table right here just goes over what we're naming different polynomials. So not so important that you memorize any of this. Really, it's just so you understand what terms I'm talking about throughout the next couple of sets of notes. So if I mention, for example, if I mention a quartic function, you can come to this table and see exactly what type of function I'm talking about. I think most of these you already know. So a constant term is just a value. So my example is 6. There are no variables with constant terms. Linear has the highest degree of 1. Quadratic has a degree of 2. Cubic has a degree of 3. Quartic has a degree of 4. And quintic is a degree of 5. I don't think I'll be talking about any functions that are higher than a quintic. So just reference this table if you hear something you're not familiar with. Standard form versus factored form. Always a big deal. Sometimes we forget how to go back and forth between the two of them. So let's start at standard form and let's work our way to factored form, and then we'll do it the other way around once we finish. So for this one, we have x cubed minus 2x squared minus 15x. If I want to factor this, I'm going to recognize that I have a GCF of x. So I can factor a GCF of x out, leaving me with x squared minus 2x minus 15. And then I'm going to look at this expression here, and I'm going to think to myself, what two factors multiply to equal negative 15, and the same two factors that add to equal negative 2? That's going to be negative 5 and positive 3. So I can rewrite this as x multiplied by x squared minus 5x plus 3x minus 15. And at this point, all I did was rewrite negative 2x as negative 5x plus 3x. To factor, I'm going to group the first two terms and the second two terms. For the next step, we have our GCF of x multiplied by the GCF of the first group is x, left over x minus 5. GCF of the second group is 3, left over is x minus 5. Now inside the parentheses here, we have our two GCFs, and we have our one common factor. So I can write this in our final factored form as x multiplied by x plus 3, which is our two GCFs, multiplied by x minus 5, which is our common factor. And this here is the factored form of the original expression. Next, we're going to look at the factored form, which is exactly where we just ended. We have x times x minus 5 times x plus 3, and we're going to convert our factored form expression back to standard form. So to do this, you need to multiply two factors together at a time. I'm going to start with multiplying these two factors together. So I'm going to distribute my value of x to both terms in the first set of parentheses. This gives me the expression of x squared minus 5x. I'm going to put parentheses around this because I am still multiplying it by that last factor of x plus 3. Then I'm going to distribute my first term to both terms in the second set of parentheses and the second term to both terms in the second set of parentheses. This is going to give me x cubed plus 3x squared. That's these first two terms being multiplied. And then right here, we have negative 5x squared minus 15x. I'm going to multiply any common terms together. The only common terms that I have are 3x squared minus 5x squared. So my final multiplied answer, or standard form answer, is going to be x squared minus, x cubed. I wrote that wrong. X cubed minus 2x squared minus 15x. And you can see for that second example I just did, I multiplied my factored form back to my original standard form. So you can easily convert between these two different forms, and you'll have to do that quite frequently when you are graphing polynomials. One of the biggest things with factored form is to just remember you multiply two factors at a time. Okay, zeros of a polynomial function. So a zero of a function is any value of x that creates a output or an f of x value of 0. Zeros can be real or imaginary. If x is a real number, then x comma 0 is the intercept. And if f of x is equal to x minus 1 in parentheses squared multiplied by x plus 2, then you can identify your zeros as 1 and negative 2. So you set each factor equal to 0, whatever you get as a solution, is your 0. You can write it as an ordered pair and graph that solution. So this box here, you can read through that. It's just typed out what I basically just said. Talks about intercepts and how you write them. For example 1, it says, given the function, determine all real zeros by factoring. Okay, we have a function that is f of x is equal to x cubed minus 6x squared minus 27x. So the first thing that I need to do in order to find my zeros is set the function equal to 0. Okay, this function here has a GCF of x. Once we factor that out, we're left with x squared minus 6x minus 27, and this is equal to 0. So we need to factor this expression, and I'm just going to jump right ahead, use the shortcut method of factoring. I know I need two numbers that multiply to negative 27 and the same two numbers that add to equal negative 6. That's going to be negative 9 and positive 3. When I factor this, I have two factors, x minus 9 and x plus 3. So total with the GCF, x times x minus 9 times x plus 3 is equal to 0. So here I factored. And then the last step for finding the zeros is setting each factor that has a variable equal to 0. I can set x equal to 0. That's one of your solutions. X minus 9 equals 0, meaning x equals positive 9. And x plus 3 equals 0, or x equals negative 3. Okay, so these numbers are called your zeros. We have a 0 at 0, a 0 at 9, and a 0 at negative 3. I'm going to list them from smallest to largest, negative 3, 0, and 9. That means if I substitute any one of these numbers back into the original equation, if I substitute any of these back into this equation, I'm going to simplify it and the answer will be 0. Example set 2 says, given the following zeros, write a possible model of the polynomial function. You're working backwards here. So if we know what the zeros are, we need to write them in its factored form. And for this one, I'm going to write two solutions. I'm going to write my factored form, and then I'm going to multiply it out to my standard form, just because different directions tell you to do different things. Within each of these examples, you'll see how to do both of them. So for number 1, we have a 0 at x equals negative 6 and 3. If that's the case, we know that we must have a function that has two factors, one of them being x plus 6, because when you set that equal to 0, you would get x equals negative 6. And the other factor being x minus 3. When you set that equal to 0, you would end up with positive 3. This here is your factored form. Now, if you were to multiply this out into standard form, that would tell you to distribute your first terms to your second set of parentheses. When we do that, we would end up with x squared minus 3x plus 6x minus 18, which we can simplify to our standard form equation of x squared plus 3x minus 18. So depending on the directions, you could be writing your function in either form. And if we do the same thing for number 2, number 2 we have zeros at -1, -1, 0, and 4. If we have a 0 at -1, that means the factor is x plus 1. A factor of 0 would be x plus 0. And lastly, a factor of x equals positive 4, or a 0 of x equals positive 4 would give us a factor of x minus 4. This factor right here, we wouldn't typically write x plus 0. We would actually write that similar to how we write a GCF. So my factored form is going to be f of x equals x times x plus 1 times x minus 4. And again, we don't write x plus 0, we just write one single factor of x. If we multiply this out into standard form, you multiply two factors at a time. We're going to start by multiplying these first two factors together. That's going to give us x squared plus x, and we're multiplying this by x minus 4. Here's where you distribute. We have x cubed minus 4x squared plus x squared minus 4x. And I can write my final standard form expression after I simplify my common terms. X cubed, negative 4x squared plus x squared is negative 3x squared minus 4x. Again, just be careful whether you are working in factored form or standard form and understand the difference between the two. Next, we're going to talk about zeros and turning points of a function. All of these key parts are helping us move towards graphing, which we will do in the next video. So, a turning point of a function. This is a point where the graph of the function changes from increasing to decreasing behavior or vice versa. So in other words, it's the place where the graph changes direction. A polynomial function of degree n being any number larger than 0, has at most n distinct real zeros and at most n minus 1 turning points. So what does this mean? Well, if we put this into perspective, we can look at this example right here. So the mathematical description says if the degree is n, then it has n distinct real zeros. If the degree is 6, that means it has 6 real zeros. It also says it has at most n minus 1 turning points. So once again, if the degree is 6, then it can have at most one less than that for turning points, which would be 5 turning points. And that's determined because it is 6 minus 1. 6 minus 1 equals 5. Okay, that's not telling you that it has 5 turning points. It's telling you that the maximum number of turning points that that function can have is 5. Example set 3 is to state the number of possible real zeros and turning points, then determine all of the real zeros by factoring. So if I'm taking a look at the two topics above, so zeros and turning points, I know that I am going to determine those from the degree of the function. The degree of this function is 3. Remember, the degree is always the highest exponent. So if the degree is 3, the number of real zeros that occurs is equivalent to the degree. That's written right here. If the degree is 3, then there can be a maximum of 3 zeros. And as far as turning points, if the degree is 3, then that's telling us that we can have one less than that for turning points. So we can have a maximum of 2 turning points. Okay, that is because it's the degree of 3. 3 minus 1 is equal to 2. That's where your turning points come from. So again, a maximum of 3 real zeros and a maximum of 2 turning points. The reason why we're going over this is because when you start graphing next class, you need to make sure you understand all of the parts. You have to understand how many turning points you can have or where the zeros are. The last part of these directions tell us to determine the real zeros by factoring. So we need to take this function here, and we need to factor solve for x. To do that, the first thing we need to do is set our function equal to 0. X cubed minus 5x squared plus 6x equals 0. I have a GCF of x. When I take that out, x squared minus 5x plus 6 equals 0. I need to factor here. So what two numbers multiply to positive 6 and the same two that add to equal negative 5? That would be positive 1, negative 6. When I set each factor equal to 0, I can get my real zeros. And I'm just going to list them. Here I'd have a 0 of 0. Here I would have a 0 of negative 1. And there a 0 of positive 6. So I'm going to list them as negative 1, 0, and 6. Number 2. So we need to determine the maximum number of real zeros and the maximum number of turning points, then find the real zeros. Our highest degree is 4. That tells us that there is a maximum of 4 real zeros. And because the degree is 4, 4 minus 1, that would be 3 turning points. That's a maximum. In order to solve for the zeros, we need to factor our equation. Start by setting x to the fourth minus 3x squared minus 4 equal to 0. If we set this equal to 0, you should all recognize from the last 2 days of notes that this is a quadratic form, but the exponent is 4. So pay close attention when you are factoring. You're going to factor the same way. You need to think to yourself, what two factors multiply to -4 and add to -3? So in this case, you would have -4 and +1. When I write my factors, instead of just writing x plus 4, I would write x squared. So I have to pay attention to my exponent. X squared minus 4x. I'm sorry, just minus 4. Writing this wrong. Multiplied by x squared plus 1. And this is equal to 0. Think to yourself, if I was to distribute these and multiply this back out, I know that I would end up back with my correct exponents. So you always need to check, make sure your exponents are matching. This first expression, x squared minus 4 equals 0. Add 4 to both sides, x squared equals 4. Take the square root of both sides, x equals plus or minus 2. This expression right here, x squared plus 1 equals 0. X squared equals -1, square root, x equals plus or minus I. The directions ask us for real zeros. This is not a real number. So I am not going to include that in my answer. My only answer is going to be positive or -2. I am not including imaginary solutions. To save time on the video today, because this is a longer note sheet, this on your own problem is completed on my note sheet posted on my website, so you can check it there. Next, we're talking about zeros, repeated zeros, and multiplicity. So a repeated zero is called a multiple zero. It's when you have zeros that happen more than once. The multiplicity of a zero is the number of times the associated factor appears. So if you have a factor that appears 3 times, the multiplicity would be 3. A multiple zero has a multiplicity equal to the number of times the zero occurs. So what does this mean? Take a look in this box. So we have zeros that happen more than once. Look at the exponents. We have this here, x minus 1 raised to the power of 3. If we set that equal to 0, we would have x equals 1, and it happens 3 times, so we would say multiplicity 3. This factor is x plus 2. Set that equal to 0, x equals -2. The exponent indicates that it happens 4 times, so we would say the multiplicity is 4. Now the multiplicity is specific to the shape of the graph. Next class, when we're graphing, the multiplicity will tell you what type of curve to make at each zero. All right, example set 4. Find the zeros and determine the multiplicity of each zero. Number 1. Number 1 is already in factored form, so all I have to do is set each factor equal to 0. X squared is x equals 0. This factor happens 2 times, so we would say it has a multiplicity. I'm going to abbreviate this as MULT, multiplicity of 2. This factor, x minus 1, has a 0 at +1. This factor only happens once. The multiplicity is 1. And our last factor has a 0 at positive 2, occurring only once, so the multiplicity is 1. Number 2 is in standard form, so in order to find the zeros, I would have to factor this. I have x squared minus 6x plus 9. This one has, or think to yourself, what two factors multiply to equal positive 9 and add to equal negative 6? And that would be negative 3 and negative 3. This factors out to x minus 3 times x minus 3, and we're solving for this, so we set them equal to 0. Because we have two of the exact same factors right here, we can rewrite this as x minus 3 in parentheses squared equals 0. If I set that factor equal to 0, we know that x equals 3. This factor happens 2 times, so we would say the multiplicity is 2. And multiplicity on the graph. This is more important next class, but real quick. Even multiplicity indicates that the graph touches or turns at the x-axis or at the associated 0. If we look at this graph, there's a 0 right here. The graph comes down, touches that point, heads back up. This graph, we have a 0, comes down, touches it, heads back in the same direction. If the multiplicity is odd, that's telling us that the graph is going to cross through at the associated 0. So in this graph, there's a 0 here, and the graph goes right through that point. There's a 0 here, and the graph goes through that point, leveling off a little bit. So odd multiplicity crosses the x-axis, even multiplicity does not. Now on all of these examples that you have here, you can see that some of them have a little bit more of a leveled off curve instead of just going straight back in the same direction, and same thing here. So the higher the degree of the function, the more of a leveled location you will have at the 0. And leveled meaning it comes up, levels off, goes back in the same direction. Okay, for the last example set, we need to use zeros and multiplicity and identify what's going on from the graph. So number 1, we have this curve here. The zeros are going to occur where the graph crosses the x-axis. So I'm just going to mark my 2 zeros. So we can either call these zeros or we can call them x-intercepts. I know that one of them happens at x equals negative 2, and I know that the other one occurs at x equals positive 2. So now I need to determine the multiplicity, and the multiplicity is determined by either crossing through the x-axis or turning at that point. So the easiest way to determine this is to draw over the graph. If I draw over the graph, am I drawing through the x-axis or am I turning at the x-axis? And you can see right there, I just drew right through that point. I'm following along, and I'm gonna draw right through this point again. Now, if I was comparing to something that would turn, that means this graph would come up to the point and then turn back in the same direction. That is not the case here. So when I traced over the graph, I drew straight through each point. Now, the straighter the line, the lower the multiplicity. Because I'm drawing straight through them, I know that I have an odd multiplicity. Because it's a straight-ish line, I'm going to say that the multiplicity, abbreviated as MULT, the multiplicity is 1 because the graph crosses. And for x equals 2, this also has a multiplicity of 1, and the graph crosses through there as well. Number 2, we have a 0 here, here, and here. So I'm indicating everywhere that where the graph either touches the x-axis or crosses through the x-axis. So we have a 0 at x equals -2, at x equals 0, and at x equals 1. If I trace through the graph, right here I'm drawing straight through at this point, so I know that multiplicity is going to be an odd number, a low odd number such as 1. Then I come back down to this point where it touches the point but heads back in the same direction. So that's going to be an even multiplicity, such as 2. And then I'm going straight through the point again. So at -2, we're crossing through the x-axis. We're going to say multiplicity 1 because it crosses. At 0, the graph bounces. So we're going to say multiplicity of 2 because it bounces, or I'm going to say turns. And at 1, crosses through again. Multiplicity 1. Okay, and for the last on your own section, I'll actually go through this table with you because it's important for graphing and understanding what each part is. So we have a function, f of x is equal to 3x plus 2, in parentheses cubed, times x minus 1, times 2x minus 4 in parentheses squared. Starting at this first factor, if I set that factor equal to 0, I'm going to end up with 3x equals -2, or x equals -2/3. This is called a 0. So x equals -2/3. The multiplicity at this point is asking us how many times does that factor occur? That factor happens 3 times. The x-intercept is asking for the actual location of that point. So where are you going to plot that point on the graph? And you would plot a point at -2/3, 0. And the behavior at the x-intercept, meaning does it cross or turn? And because the multiplicity is 3, that's an odd number. That tells us that it's going to cross. So, zeros and x-intercepts are essentially the same thing. One of them is the location on the graph. One of them is just the answer. Multiplicity tells you what the behavior is on the graph. Okay, the next factor, x minus 1, set that equal to 0. Your solution would tell you that x equals 1. This factor only happens once, so the multiplicity is 1, which is an odd number. On the graph, we would plot this point at 1, 0. And because it's an odd number, it would cross at the x-axis. And the last 0 occurs at 2x minus 4. When we set that equal to 0, we would have x equals 2. This factor has an exponent of 2, so we know that the factor occurs twice. 2 is an even number. This point is located at 2, 0, and because it's an even number, it turns at the x-axis. Alright, after this lesson, you have several tests and tools to aid in graphing polynomial functions, which is what we will be doing on tomorrow's note sheet.